Hey guys, so I'd given you this derivation as part of your homework. That is, you had to derive the formula for electric field due to a uniformly charged linear wire. So let me do this derivation here because the formula which will be deriving here will be useful in many cases in most of your homework questions as well, right? Okay, so let me define the case. We have a uniformly charged linear wire, and it's given that the linear charge density of this wire is lambda. We need to find out what will be the electric field due to this wire at a random point P, which is located d distance away from it. And rather than describing the length of the wire, we'll be writing the formula in terms of these angles, alpha and beta, which is kind of an indicator of the length of the wire over here, right? So the case is simple. We have a uniformly charged linear wire. Linear charge density is given lambda. We need to find out what will be the electric field to this linear charged wire at a point P, which is located d distance away from it. So our approach is straightforward here. Once again, this is just an integration based question. So we'll have to go with the same idea. That is, we'll imagine this wire to be made up of many small point charges. And the way we select a small point charge over here is at a distance of x. Let me select a small portion subtending or having a small length dx. And let the value of this point charge be dq. The value of dq will be equal to lambda into dx. Right? Now we'll calculate what will be the field due to this dq at this point P. At this point P, which is located over here. So your direction of field will be, since we're assuming this to be positively charged, your direction of field will be radially outwards. So your direction of field here will be in this way. So let me call that value of field as dE. And what will the value of dE be equal to? We can say dE is equal to nothing but k into lambda into k into your charge divided by r squared. So k into lambda dx divided by r squared, where r over here is nothing but this distance, right? Okay, so now the idea over here is now to add all these fields up to get the total field vector. But one thing we need to realize over here is we are adding up vector quantities. So before we go ahead with integration, we also have to check what about the directions of a field due to all the point charges. So here, all the point charges create fields in different directions. This will be creating a field in this direction. This will be creating a field in this direction. And there's no symmetry over here. If you notice, this point P is not located symmetrically with respect to point P. So there's no cancellation of components as well. So here you'll have both the components of field. Here you'll have both your x and y components of field in this case. So if you have to find out what is the net field in this particular scenario, we can only calculate the net field by adding up all the x components of field and adding up all the y components of fields. Right. And what will be your x component of field here? So we already calculated what DE is. Let me assume this DE makes an angle theta with the x-axis. So your x component of field will be equal to DE cos theta. And your y component of field will be equal to DE sin theta. So here we'll have to integrate these components separately because that's how you add up vectors, and integration ultimately is nothing but summation. So that's how you'll have to integrate vectors as well. Right. So now proceeding ahead with the calculation, we'll calculate x component and y component separately. So let me calculate the x component first. So x component of field will be equal to integral d cos theta. So we already calculated what d is. D is equal to nothing but k into lambda dx divided by r squared. And we can find out the value. R keeps on varying with x, right? So it's better to write r in terms of x. And we can find out what the value of r is from this right angle triangle. R is the hypotenuse in this right angle triangle. So r will be equal to under root of x squared plus d squared. But since we need a square of it, this will just be k into lambda dx divided by x squared plus d squared multiplied with cos theta, right? So this angle is theta. So this angle will also be equal to theta itself. So what will cos theta here turn out to be? Cos theta here turns out to be nothing but d divided by under root of x squared plus d squared, right? So here we are integrating all the x components of field being created by all the point charges, right? So now coming to your limits of integration. So let me define this length to be L1. Let me define this length to be L2. So limits of integration will be from x is equal to minus L2 to x is equal to plus L1, right? So now solving the integration. So taking all the constants outside, k, lambda, d are all constants. What we're left with over here is integral of dx divided by x squared plus d squared whole power 3 by 2 with x is equal to minus L2 to x is equal to plus L1, right? So to solve this integration, we'll have to use a substitution method. So here we'll have to imagine x is equal to some d tan phi. So if x is equal to d tan phi, then dx will be equal to d secant squared phi d phi. Then substituting this in the integration, we'll get, so our integration, our x component of field was integral. So the constants which we had were k lambda d, integral dx by x squared plus d squared whole power 3 by 2. And now substituting our values. So we'll get k lambda d. So we are substituting x as d tan phi. So dx turned out to be d secant squared phi d phi. And the denominator will become d squared tan squared phi plus d squared will become d squared secant d squared tan squared phi plus d squared will become equal to d squared secant squared phi with the whole power 3 by 2 will become d cube secant cube phi, right? So this will become equal to k lambda d integral 1 by secant phi d phi, which is nothing but cos phi d phi. D is a constant, so that can be taken out. We have d by d cube, so that will become equal to by d squared. So we'll have a d squared outside over here. So this integration basically becomes equal to k lambda by d. Integral cos phi is nothing but sine phi. Integral cos phi is nothing but sine phi over here, right? Okay. Now, here, okay. Then what is sine phi? And now going back to original substitution, tan phi was equal to x by d. Tan phi was equal to x by d. So what will sine phi be equal to? Sine phi will be equal to nothing but x by under root of x squared plus d squared. So bringing back our original substitution, we'll get k lambda by d, x by under root of x squared plus d squared, with x value varying from minus L2 to plus L1. So this becomes equal to k lambda by d, L1 by under root of L1 squared plus d squared, minus of minus L2, so it becomes plus L2 divided by under root of L2 squared plus d squared. Right? We could have simplified this calculation a bit, but it's okay. We're going about it with the general way of how we actually solve these kind of integrations. Okay. And now we'll now try to notice this right angle triangle. So in this right angle triangle, so in the result which we got L1 by under root of L1 squared plus d squared, and we got L2 by under root of L2 squared plus d squared. So what is L1 by under root of L1 squared plus d squared? That will be equal to sine alpha. So we can write this result in terms of k lambda by d of sine alpha. And if you notice in that triangle, this was L2, this angle was defined as beta, this distance was BD, so this is under root of L2 squared plus d squared. So this will become equal to sine beta. Right. So we have calculated one component of electric field, and we have calculated that as the x component of electric field. But if your orientation of the rod changes, your x and y changes, so it's better to remember this as electric field component perpendicular to the rod. Right. So we derive the formula for what would be electric field due to a linear charge rod, and its electric field component perpendicular to the wire will be equal to k lambda by d sine alpha plus sine beta. Right, so this will be helpful to solve many numericals because as you can notice, your integration is slightly lengthy over here. Okay, then let's calculate the other component, which was your y component of electric field. So y component of electric field was equal to integral d sine theta. If we remember, our d was equal to k into lambda into dx divided by x squared plus d squared. And what was sine theta in the right angle triangle? Sine theta was opposite by hypotenuse. So sine theta will be equal to x by under root of x squared plus d squared, right? And once again, your limits are from x is equal to minus L2 to x is equal to plus L1. Okay, so once again, removing constants from this integration, which in this case is just k lambda. So we end up with integral x dx divided by x squared plus d squared whole power 3 by 2, right? And to solve this integration, I hope you recognize this pattern. Here it's better to take x squared plus d squared is equal to some z squared. Then we'll get 2x dx is equal to 2z dz. So x dx is equal to z dz. So making use of this integration, making use of the substitution in the integration, we will get this value to be equal to, so k lambda. So instead of integral x dx, we'll now have z dz. And x squared plus d squared is z squared. So z squared whole power 3 by 2 will give me z cube. So this becomes equal to k lambda integral dz by z squared, which is equal to nothing but k lambda of minus 1 by z. And bringing back our substitution, so z was equal to under root of x squared plus d squared. So it will be k lambda by minus under root of x squared plus d squared, right? And our limits again is x is equal to minus L2 to x is equal to plus L1, right? Okay, so what will this turn out to be? So here we'll get this term to be equal to, we'll get k lambda of minus 1 by under root of L1 square plus d square plus minus of minus will become, sorry, so here minus of minus will become plus, so this become plus 1 under root of L2 square plus d square, right? And again, we'll try to write this in terms of alpha and beta. So what we'll do a simple simplification over here. We'll multiply and divide by d. So I'll get k lambda by d of minus d by under root of L1 square plus d square plus d by under root of L2 square plus d square. Okay, and now if you remember the right angle triangles which we had, your minus d by under root of L1 square plus d square is nothing but, so let me draw a rough version of the diagram. So this was your diagram, this was your alpha, this was your beta, this is d. So this was L1, this was L2. So d by under root of L1 square plus d square is nothing but cos alpha, and d by under root of L2 square plus b square is nothing but cos beta. So we'll get this result to be equal to k lambda by d of cos beta minus cos alpha, right? And even though I mentioned this as y component of electric field, it's better to remember this as your electric field component parallel to the rod, because again your orientation can change. So electric field component perpendicular to the rod is equal to k lambda by d of cos beta minus cos alpha, right? Okay, so let me summarize this entire thing. So we have now calculated the formula for electric field to a uniformly charged finite wire or rod, uniformly charged wire, let me describe it that way. So we had found out what was electric field to a uniformly charged wire at a point P. And we have written this formula in terms of d, alpha and beta. So let me describe those terms once again. So d was your distance, alpha and beta were your angles separated by the end points of the wire with the perpendicular. So this was alpha, this was beta, this is d. Right, so the electric field component perpendicular turned out to be k lambda by d sine alpha plus sine beta, and the electric field component parallel to the rod turned out to be k lambda by t cos beta minus cos alpha, right? So here, because we have a negative sign, there can be a confusion arising as to which angle should I be very careful with what I select as beta and what I select as alpha. So my suggestion over here is, we know, let's say so let me describe this once again in terms of L1 and L2. So if L2 is far greater than L1, if L2 is not far greater, if L2 is greater than L1, then I know that I'll have an electric field component. And if this is positively charged, then I'll know that I have more charges in the lower half than I have charges in the upper half. So my electric field will be having an upward component, right? So we can always take any angle as beta, any angle as alpha, because you can always figure out what will be a direction of electric field parallel to the rod using this idea. That is, if wherever I have more positive charge, there I'll have a higher upward component. So my electric field parallel will be in the upward direction. If L1 was greater than L2, then that means the electric field in the downward direction will be more over here, right? So we don't need to worry about what is beta and alpha. We can always take the positive value of it and figure out the direction of the electric field component parallel to the rod using this idea, right? Okay. So there are some cases where we can again make use of this to get some more results. So let me derive those results quickly as well. And that is, we can derive the formula for electric field due to an infinite uniformly charged wire. So if I have an infinite uniformly charged wire, so that is going on till infinity. And now I need to find out what's electric field at a point P, which is located d distance away from it. Right. So we can make use of this formula which we have derived over here. And that is, now I know the distance. All I now need to find out is alpha and beta, right? So because this is infinite, in order to join the endpoint of this wire to this, I'll have to go almost parallel to this wire only. I'll have to go almost parallel to this wire. So this is how I join the point P to the end point of this wire. Similarly, because the other half is also infinity, again, I have to go almost parallel to this wire to join the end point of this wire to infinity as well. So alpha and beta in this case, both turns out to be equal to 90 degrees. Alpha is also 90 degrees, beta is also 90 degrees. So from this, you can derive the formula for electric field to an infinite linear charge. And electric field to an infinite linear charge turns out to be. So we'll only have the perpendicular component. So let's calculate both the components over here. So electric field perpendicular to the rod will be equal to k lambda by d sine alpha plus sine beta, which is equal to sine 90 plus sine 90. So 1 plus 1 is 2. So we'll get electric field along the perpendicular component to the rod to be equal to 2k lambda by d. So we'll have an electric field along this direction, and that will be 2k lambda by d. And what about electric field component parallel to the rod? Because alpha and beta are both equal to 90 degrees over here, this will be k lambda by d of 0 minus 0, cos 90 minus cos 90. So from this, you can derive the formula for electric field to an infinite uniformly charged wire. And that formula is nothing but you'll only have an electric field component perpendicular to the rod, and that value will be equal to 2k lambda by d. Right? Similarly, one more result is electric field to a semi-infinite wire. Electric field to a uniformly charged semi-infinite wire. So these are two cases which will very commonly come across. You can just remember the formula for now for a straight rod, and then you can derive the values for infinite and semi-infinite from this. Right. So what do you mean by semi-infinite precisely in this case? By semi-infinite, we mean that we now have a wire, which is again uniformly charged, so has lambda, and we are finding out electric field at a point P, which is located at the end of this wire, which is located, perpendicular to the end of this wire. So your diagram here would look like this. So now we need to calculate electric field at this point P. Right. So once again, we can make use of our formula which we had derived over here, and that is I'll have an electric. We can derive the formula for electric field component perpendicular. We can also derive the formula for electric field component parallel. Right. So for that, we need alpha and beta first. So let me first find out what alpha will be equal to. So alpha once again means we'll have to join the endpoint of this wire. We'll have to join the endpoint of this wire to this point P. Right. But where is the endpoint of this wire located? The endpoint of this wire, the upper end point of this wire is located at infinity. So to connect it, I have to go almost parallel to this wire. So alpha in this case also turns out to be 90 degrees. Alpha in this case also turns out to be 90 degrees. And where is your lower end point of the wire located? Your lower end point of the wire is located here itself, right? So here, to join the end point of this wire here, I just have to draw this line. So what angle does this make? Here beta will be equal to 0 degrees. So making use of both of them now in this formula. So electric field component perpendicular to the rod is k lambda by d sine alpha plus sine beta. So that will become sine 90 plus sine 0. So that will be equal to just k lambda by d. And electric field component parallel to the rod will be equal to k lambda by d cos beta minus cos alpha. Again, so here, let me show you that it doesn't matter what you take as alpha and beta. So let me write this cos 90 minus cos 0. So I've reversed the order of alpha and beta just to show you that it doesn't matter. So here we'll get a negative answer, right? So as I mentioned, don't worry about the negative sign, just take the positive value of it, because you can always figure out what's the direction of electric field over here, right? So because this is a positively charged rod, the electric field perpendicular to the rod will be in this direction. It'll be away from the rod. So this is your electric field component perpendicular to the rod, and its value was k lambda by d. Now, because once again this is positively charged, every point charge which I have over here will create an electric field in the downward direction. Will create an electric field in downward direction. So here I'll have an electric field component parallel to the rod in the downward direction, and that value will be equal to k lambda by d. Right. So these are two important results. So these are three important results actually. The three important results we have to make sure we remember in this case is electric field to a finite wire that had a parallel component and a perpendicular component. That was k lambda by d sine alpha plus sine beta, k lambda by d cos alpha minus cos beta. Then from that we can derive the formula for electric field to an infinitely charged wire and even a semi-infinite wire. One thing to remember, in semi-infinite wire, your point P has to be located exactly at the end point. If it's not located at the end point, like if it was located at some point over here, so even though you might say it's semi-infinite, this will not fall under that category. You again have to derive the formula using alpha and beta, right? So hopefully this derivation is useful. We'll be making use of this formula in many cases. So that's why I've done the derivation for you guys over here, right? See you guys.